Okay, we're going to mimic the work of the one that gets credit for originally is a guy named Compton. He was looking at the photoelectric effect, and he said, okay, we can think about a particle of light, a photon, traveling with some particular wavelength. It crashes into a metal, so this little rectangle trapezoidy thing, parallelogrammy thing is going to represent my piece of metal. That photon is eventually going to crash into an electron in the metal. They interact kind of like a classical collision, transfer of momentum, a splitting of energy, and that electron gets ejected with some kinetic energy, and even sometimes a little bit of light energy comes off of the metal from the photoelectric effect. But really what this guy was doing was he was thinking about it like a classical collision, and classical collisions are all about momentum and energy. If we think about the photon, if we try and talk about its momentum, momentum is always mass times speed. But because it's a photon, it's moving at the speed of light. So we can say that the momentum of that photon is mass times c. Collisions are also about the energy. Planck said that energy of a moving photon was h times f. We're looking at it in terms of wavelengths, so we can apply the wave equation. We know v is equal to f times lambda. It's moving at the speed of light, so c equals f lambda, or lambda equals f over c. So we get, oops, I did that upside down, didn't I? F equals c over lambda. So we get E equals hc over lambda. Now a little cheat to get us farther. I don't think Compton did it this way, but a little shortcut we can do to get to the same answer as Compton is if we take what Einstein said E was also equal to mc squared. So we can say m is equal to E over c squared. And we have Compton's work that says E is equal to hc over lambda. So if we combine those two, we can say m is equal to E, but instead of E, I'm going to write hc over lambda all over c squared. If I clean that up, the c on the numerator cancels with one of the c's on the denominator. Take a second, convince yourself that you agree that this turns into m equals h over lambda times c. Now we're almost there. We know that momentum is m times c, and we just figured out that mass was h over lambda c. If we combine those two, we can say that momentum equals h over lambda c, all multiplied by c. The c's are going to cancel. We get this crazy equation. Momentum equals h over lambda. This is a very, very simple looking equation, but it's rather deep. What it does is it calculates the momentum of a photon. If we know the wavelength of something, we can plug that into there, and from the wavelength, we can figure out the momentum. What's neat about that is photons have no mass, so we couldn't use our normal, even though I wrote it down up here that momentum was mass times speed, we can't use that equation to get the momentum of a photon since the mass is zero. The only way photons can travel at the speed of light is if they have a mass of absolutely zero. So this cool little equation allows us to connect the particle property of momentum to the wave property of wavelength.